Good afternoon and welcome to today's lecture on algorithms and data structures. In our last lecture, we finished selected topics and concretely we looked into prime numbers and the Bloom filter. And now we have come almost to the end of the course because we've seen lots of classic algorithms and data structures, be it lists, trees, hash tables. We saw complexity, recursion, sorting, graph problems, and all these data structures we looked at are essentially some kind of graph. And most of the theory we have seen so far is decades old. So the theory around trees or sorting, a lot of that work was done between the 60s and 70s, maybe the 80s. And there were some topics that are maybe a little bit newer, but most of those foundations were proposed long time ago and they have been established very well. And this is where a typical introduction to algorithms and data structures would end. We've already done quite a lot, including the selected topics. But today we are looking at some cutting edge topics around algorithms and data structures, concretely quantum computing. Quantum computing comes with the promise of solving certain computational problems substantially faster, and faster not in terms of a constant factor, but certain problems can be solved with a quantum computer in a better complexity class. And that's super interesting. So today we will look at so-called qubits, which are the fundamental unit in a quantum computer, a quantum bit or a qubit. We will see how we can do logic operations on quantums. We will see we will do logic operations on qubits, and we will see quantum computers that concretely implement this. And then we'll look at selected quantum algorithms that actually come with a speed up. In order to take full advantage of this chapter, what you need to know is logic gates, which you definitely know from your introduction to computer science. So we have binary variables like A and B, and we can have an AND gate, an OR gate, or a NOT gate, and eventually implement some kind of Boolean logic function. That's a prerequisite. We're going to extend this to qubits, not just to bits, as we've done it before. And you also need complex numbers. So a complex number or complex numbers are a set of numbers that extend the real numbers, because a complex number has two components. It has the real component A and another component B, which is a real number, but we multiply B with I, which is the imaginary number. And if you square I, you have -1. Something you cannot do with the real numbers, because if you square a real number like 0, you have 0. If you square a positive number, you get a positive result. If you square a negative real number, you get a positive number. But with this imaginary one, I squared, we establish that it's -1. So I squared, and you take the square root would be the square root of I squared would be the square root of -1, which would be I. And this is something you cannot do with the real numbers. Are you all okay with complex numbers? Maybe just send me some signal here in the chat if you're okay with complex numbers or not. Something that you should have seen also in your introduction to maths. And these are the prerequisites. And now, what is quantum computing about? There's a lot of hype about quantum computing in recent years in the news, and you hear all sorts of strange stuff that quantum computers would replace all of today's computers, that quantum computing would probably be dangerous and this kind of stuff. Today, we'll have an informed look at that, and we will see if those claims are actually true or not. But very importantly, quantum computers will not replace all of our traditional computers. Rather, they address a certain niche of problems. So what we will see in the coming decades is probably coexistence traditional computers and quantum computers. And quantum computing takes advantage of quantum mechanics in order to perform computations. Who of you studied quantum mechanics before? Maybe, for example, at the end of high school in physics or in some other occasion. If you have come across quantum mechanics, send us some positive reaction. If you have never come across quantum mechanics before, send us some negative reaction, please. Oh, mixed answers, but you don't need to be an expert in quantum computing or in quantum mechanics for this today. Rather, we will establish the foundations, and this chapter is anyway just an outlook at the end of the algorithms and data structures course. And now, if we do quantum computing, we need concrete computers. Those are quantum computers, and they take advantage of quantum mechanics so we can establish quantum parallelism. And quantum parallelism allows us to do massively parallel computations. And this gives us an advantage to traditional computing for certain computational problems. There are certain computational problems around optimization, some for machine learning, some for encryption and decryption. And maybe you heard about this, that as we get more powerful quantum computers, we may be able to crack today's encryption sometime in the future. And that's why IT vendors are slowly, or they have started to move to new encryption algorithms. But that's something we'll see later. When it comes to machine learning, quantum computers look promising that we can actually run computations much faster, maybe learn better models from less data. And the good thing is, the initial theories around quantum computing were established in the 1980s. Today, we have real quantum computers available. They may be limited, but at least we can run some computations nowadays. I personally think that we probably still need decades until we get larger quantum computers that address more and more real-world usages. And I think that the computing architectures we have in today's computers will probably still live for a very long time, because what we have, in fact, in traditional computing nowadays is a combination of RISC and CISC architectures. And this is super helpful because our computers today, they are highly generic and we can use them for lots of computational problems. And it's quite easy to program today's computers to solve a problem. But quantum computers, they address a specific niche of problems. And as we get more powerful quantum computers in the foreseeable future, probably we have more and more applications of quantum computers, but the large majority of computations will probably be still done by regular computing. Now, the fundamental unit in a quantum computer is a so-called qubit. As you remember from your introduction to computer science, in a traditional computer, we have bits, and the bit is either 0 or 1. A quantum bit or qubit, so sometimes a qubit you write like this, qubit or quantum bit, or just a q and a bit. This is the fundamental unit in a quantum computer. And the qubit can be both in 0 and 1 at the same time. So this is some parallelism with a certain proportion in 0 and 1. And now this gives us parallelism. What we have is, in fact, the so-called superposition. That's the term you would see from quantum mechanics. And something that becomes very interesting is, now imagine you combine 10 qubits. And if you combined, say, 10 regular bits, each would be either 0 or 1, you would have one state in total in these 10 bits, a state that is 10 bits, but each bit is either 0 or 1. Now, with a quantum computing approach, we have 10 qubits combined, and each qubit can be partially in 0 and 1. So what we can do is, with computational operations, we can work on 2 to the power of 10, so 1024 states at the same time. While with a traditional computer, with bits, you would work on one state at a time when you work on these 10 bits together. But with a quantum computer, you'd be working on 1024 states at the same time with your operations. So this gives us massive parallelization. And by taking advantage of quantum mechanics. And for the next part, I will quickly switch to the whiteboard and I'll show you a little bit of the mathematics behind quantum computing. Will be continued. So now let's look at how we can mathematically describe a qubit. We denote a qubit in the following notation. Say A, but we don't just write A, we use this notation here. And this one would be called A ket. And I'll just tell you how to pronounce this. So this would be A ket, K-E-T. So not cat like the pet, but this is from the so-called bra-ket notation, which is very common in quantum mechanics, bra-ket notation. We use this A ket to denote a single qubit. And what we want to do is A will be partially in state 0, and it will be partially in state 1. And this here would be pronounced 0 ket and 1 ket. And they are partially now, our qubit is partially in 0 and 1 at the same time. And what we need for this are so-called complex probability amplitudes. With 0, we often denote this as an alpha and a beta for the 1. And in blue, I'll just write down what they are called. These are so-called complex probability amplitudes. And all of this is also written in the slides, so just develop it now step by step with you. And what does 0 and 1 ket look like? Eventually, now just delete this here so I have more space for the bra-ket notation. Eventually, this can be represented in terms of vectors. So we have our alpha and our beta, and the 0 ket can be denoted as a vector. It's a column vector of 1, 0, and then 1 ket as 0 and 1. So the first entry stands for the 0 component, and the second entry stands for the 1 component. And so alpha times this plus beta times this, we could also just write this as a column vector, which is alpha and beta. Are you all okay with the notation up to here? Right, just confirm with some positive or negative reaction, but that looks okay. Now, why is this called a complex probability amplitude? So the probability amplitude, simply speaking, means how much the qubit has a 0 component and the other amplitude, how much it has a 1 component. But alpha and beta are complex numbers and are not real numbers. And what we are doing here, in fact, is called complex linear algebra, because we use linear algebra structures like a vector and later matrices, but we don't plug in real numbers. We can also plug in complex numbers. So we talk about complex linear algebra, the linear algebra structures on complex numbers. But in order, now you wonder, what does alpha and beta need to look like? There is a constraint, and the constraint is that your alpha modulus squared plus your beta modulus squared must be 1. Do you still remember what the modulus of a complex number would be? Maybe give me some reaction if you still remember what the modulus of a complex number is. So what does this notation mean here? It's if you see alpha as a complex number, or alpha is a complex number, you can see a complex number also as a vector, and then this would be the length of the vector, or the absolute value of the complex number. So remember, there's one example here. Alpha would be 1 plus 5i. Then the modulus of alpha would be the square root of 1 squared plus 5 squared. So 1 plus 25, the square root of 26. Does that ring a bell about the absolute value of a complex number with the length of the vector if you interpret the complex number as a vector? Good. So see positive reactions. And now this says the modulus of alpha squared plus the modulus of beta squared must be 1. And only if that's the case, then we have a valid qubit. This constraint here comes from quantum mechanics, because in quantum mechanics, you can have not just 2 dimensions, you can have way more dimensions, and then you can generalize this here. But this is just a consequence of quantum mechanics, something that we are not deriving now in step by step. We're just applying quantum mechanics here, and quantum mechanics says that this qubit would be a valid qubit if alpha, or modulus of alpha squared plus the modulus of beta squared summed up must be 1. And we've just seen one example of a complex number and its modulus. This is the very beginning now of what a qubit looks like. And I'll briefly switch back to my slides. All I have shown you is also available here. And now we have qubits, or a single qubit and a second qubit and a third qubit. And we want to do operations on those qubits. And for this, we need quantum logic gates. So as you have bits in traditional computing, you do fundamental operations on a bit. Say you can invert a bit, so 1 flips to 0 and 0 flips to 1, so the NOT gate. You can have an AND gate or an OR gate. These are the fundamental operations in traditional binary computing. And here in quantum computing, we need different quantum logic gates. And for now, we just call them quantum logic gates, or quantum gate just means the same. These are the fundamental operations we need in quantum computing. And eventually, these quantum gates, they are the building blocks of our quantum algorithms, because we just combine various fundamental operations in order to do the computations that we want. And this is what you also learned in your introduction to computer science, how you would do this with binary variables, so with bits. One thing that is different here is will have different gates. You will see them in a moment. But the days when you needed to combine individually gates in a piece of hardware, those days are long gone, because nowadays we have high-level programming languages like Python, Java, C++, and you don't, what you do is you write high-level code, and eventually it somehow gets compiled to assembly code, and eventually this will be these low-level operations, but you don't need to be thinking anymore too much about these low-level operations. Sometimes you have to, but most of the time not, because you write very abstract high-level code. And maybe 60 years ago, you had to think about these low-level operations on your own, how to combine bits with low-level operations in order to build more powerful functions. With quantum computing, we are still in very many cases at this very low-level approach that we need to think about individual qubits and how to combine them and which low-level operations to run. So we do not have these powerful abstraction layers, but rather we work on a very low-level way. And this is something that limits quantum computers or quantum computing today, because we as software engineers, we cannot just use some high-level language, but rather we need to think in terms of these low-level operations. And for these low-level operations, we don't use bits, but we use quantum mechanical effects. So we see coming up with a new algorithm can probably be very challenging. Now, what are some of those low-level operations? The simplest one is a so-called NOT gate. We have a NOT gate in binary computing, and we have the same NOT gate just generalized in quantum computing. The traditional NOT gate in binary computing flips your 0 to a 1 and a 1 to your 0. And now we have our qubit, which is alpha times 0 ket plus beta times 1 ket. And we apply the NOT gate. The NOT gate is often written as an X in quantum computing. So X could be seen as a function, and we apply this to our qubit. And what it does is it flips alpha and beta. So the alpha, that was the complex probability amplitude for 0 ket, becomes this for 1 ket. And so becomes beta, which was the complex probability amplitude for the 1 ket, the one for 0 ket. So we just flip these two probability amplitudes. It turns out you can represent our quantum operations as matrices. And our NOT gate, our X gate, can be represented as this matrix, which is a 2 times 2 matrix, which is 0 and 1 and 1, 0. And now, if you take your matrix X and you multiply this with a concrete qubit, I think I'll show you this again on the iPad. So then we can develop this together step by step. So this is the X gate. We said X, so 2 times 2 matrix, 0, 1, 1, 0. And now we have a qubit, and say our qubit, which is A ket, we could say is something like 0.6 and 0.8. These are now not real numbers, but they are complex numbers, but they only have a real component, but they're still complex numbers. And A ket is a valid qubit because, remember our constraint, we would take the absolute value or the modulus of this and square it plus the modulus of this and square it. And if you have a real number, which is 0.6, or this real component 0.6, which is the real component of our complex number, and you take its modulus, the modulus is just 0.6, but we square the modulus, so 0.6 squared, and we take the modulus of 0.8, which is 0.8, and square it, then this is 0.36 plus 0.64 is 1. So this is a valid qubit. It's a very simple one. Just in order to keep it simple, we only put the real component here, not the imaginary component. Um, but a cat is a valid qubit. And now I want to apply this NOT operation to my qubit, and X is a matrix, and I would multiply my vector a cat from the right. So 0.6 and 0.8, I multiply from the right with my matrix X. Remember, X is 0, 1, 1, 0. Then multiply from the right my vector 0.6 and 0.8. Then what I get is eventually, so I have this row and this column. Eventually it will be a match for these two. So it will be 0.8 and 0.6 will be the second component. So what I see is I have just flipped these two complex probability amplitudes, and that's what the NOT gate does. There are more fundamental operations. One that is very famous is the so-called Hadamard gate. And the Hadamard gate looks something like this. We will not discuss this today in detail because it's just an overview today in the last lecture. But this Hadamard gate is actually a gate that creates a superposition. Because when I have my quantum computer, the quantum computer somehow must be accessed from outside, from our traditional world. And what I need to feed in are basis states. So for example, I have an entry, which is a 0 cat, and somehow I want to create a superposition from that. And in fact, using this Hadamard gate, I will get, if I put in a 0 classical value from outside, I will get an equal superposition of 0 cat and 1 cat. And you can try this out on your own if you, for example, take H and you multiply 0 cat from the right. Because you have H here, and you've seen before what 0 cat looks like. So you could try this out. You just multiply 0 cat from the right with H, and you would eventually get something like this. So you can try this at home. The Hadamard gate also does, if I put in a 1 cat, it would map this to a 0 cat minus a 1 cat divided by the square root of 2. The square root of 2 comes from this Hadamard matrix. So 1 divided by the square root of 2 is a constant factor for each of these entries. And eventually, if you try these calculations on your own, you will see that this divided by the square root of 2 is just a normalizer. So we actually have valid qubits because we said the modulus of alpha squared plus the modulus of beta squared must be 1. And this is what these normalizers lead to. These normalizers in the Hadamard matrix. So this Hadamard matrix, what it does is it creates a superposition, and we need superpositions in order to take advantage of quantum mechanical effects. So the Hadamard gate is something you would use quite early in a quantum algorithm because you put in classical values, and we don't just want to be using classical zeros and ones because for this we have traditional computers, but rather we want to create a superposition, a parallelism, and then work with other operations and do what the algorithm is supposed to do. And there are many more fundamental operations. We're not looking at them today, but they're always expressed as a matrix and our state as a vector. And we'll switch back to the slides. So I have just shown you this Hadamard gate or Hadamard matrix. And Actually, I just noticed I made a minor mistake, but I'm not switching back to the slides now. The last entry is obviously a -1, not a 1. Well, I'll quickly switch back to the I'll quickly switch back to the iPad just to fix it in case we need it again. So very important, this is a -1, and it's correct in the slides. So, what does a quantum algorithm look like? A quantum algorithm is eventually a sequence of quantum operations, and the quantum algorithm would start with classical bits 0 or 1 that I feed in. Then I have whatever quantum operations in here. Some of them will probably be a harder mod matrix because I need to create superpositions in order to take advantage of quantum effects. There are other quantum operations, so this block here could be a harder mod or something else. This is a so-called C knot, a conditional knot. What they do exactly doesn't matter for this introductory lecture today, but I will do a series of quantum operations, and then I need a result. And for these 4 qubits, I have at the end a sign like this. And this sign means it's a so-called measurement. Now, what is a measurement? When I run these quantum operations, and there could be more operations in here, eventually I need an output from the quantum computer. And the output that I need in my traditional world will be again 0 or 1. It will not be some superposition. So a measurement turns the superposition into a classic value. Now imagine I have a superposition in this qubit, which is very, very close to 1. So it has a very large complex probability amplitude for 1 and a very small one for 0. What would you get if you do a measurement? Would you get 0 or 1? And I'm repeating, so what you think in the chat, send it if you think the measurement would return a 0 or a 1. My complex probability amplitude for 1 is very, very large, and for 0, it's very, very small. I want to see your guess. What you think if I get a 0 or 1, if you send this to the chat, please. I'm waiting for your answers in the chat. One person writes a 1, one writes 1 question mark. Well, the question mark is probably a helpful addition because the measurement is probabilistic. So if my qubit is very, very close to 1 and just has a small component for 0, if I do a measurement, most likely it will be a 1, but could be a 0 as well because it's probabilistic. So what I often need to do is I need to run the same quantum experiment many, many times. And what I will get is a distribution of outputs. And the most likely output will appear more often than the unlikely one. So such a quantum computing experiment, you typically not just run once, but you run it many, many times to get a distribution of the outputs. I know this is, well, you've done some non-deterministic or stochastic algorithms, but the quantum computing world is highly stochastic, highly non-deterministic. And when you do the measurement, we say that our qubit collapses. And collapsing means the quantum state, the superposition, is gone. We will have a classical value in the variable. We cannot go back to the superposition, so it collapses. And then you need, if you want a quantum state again, you need to run the experiment again. So you cannot measure the same qubit multiple times. Once you measure it, it collapses, and you only have a classical value left. All of this are consequences from quantum mechanics. Now, a few words about our matrices. We've seen this matrix here for the Harder-Nott gate. We've seen this matrix for the NOT gate. And maybe you're wondering, what kind of matrices am I allowed to use to represent my operations? It turns out our quantum gates are represented by so-called unitary matrices. Now, what is a unitary matrix? If I have a matrix U and I multiply it with its so-called adjoint, the adjoint, and I'll show you in a moment what the adjoint is. We have this dagger. So this is pronounced as dagger, U dagger. If I multiply U with its adjoint, so U times U dagger, or U dagger times U, this must lead to the identity matrix. Who of you remembers what the identity matrix is? If you remember the identity matrix, send a positive reaction and then maybe send it to the chat what the identity matrix looks like. I'll wait for your answers while I'm switching again to the other screen. Get a positive reaction, but then I'll see if we get an answer in the meantime. So the identity matrix I, for example, for 3D or for say 2D, would be a matrix that has ones in its diagonals, in its first diagonal, but all other entries are zero. So sometimes it is written as I2 for a 2 times 2 matrix, while I3 would be 1, 1, 1, then 0, 0, 0, 0, 0. This is the identity matrix, and we got the right answer here in the chat. Now, a matrix is unitary if U dagger times U is the same as U times U dagger. It's important this is a dagger, it's not a transpose, and we will see very soon what this dagger does. This is the identity matrix. And I'll tell you later why we need this. Now, let's look at what this dagger actually does. It's the so-called adjoint of a matrix. And the adjoint means the following. So let's say I have a 2 times 2 matrix. It's A, B, C, and D. And I apply the dagger. Then the adjoint of this matrix is first of all a transpose. So A and D stay, but B and C are flipped. Plus, I have this bar on top. And remember that A, B, C, and D are complex numbers. Do you have a clue what this bar on top may mean? If you have an idea what this bar on top may mean, let us know. I'm sorry, it's back. So we got a few suggestions. And the suggestion was that it's the conjugate. And that's correct. The conjugate means, so the conjugate means I have A, which is well, let's not call it A, let's call it, for example, C for complex, is A plus B times I. So the conjugate C bar would be A minus plus I. So we just changed the sign of the imaginary part. So we've changed this here. So the adjoint of a matrix, the 2 times 2 matrix is A, B, C, D. Then its adjoint is we do a transpose, so B and C get flipped, but we also get the conjugate of each entry. So in each entry, we change the sign of the imaginary part. And then if U dagger times U is the same as U times U dagger, and this is the identity matrix, then a matrix is unitary. And for example, our NOT gate is unitary, and the Harder-Matt gate is unitary too. And I'll tell you soon why these unitary matrices are so important in quantum computing, but we'll do a quick assignment about the adjoint together. So I have a 2 times 2 matrix, say 6 minus 3i, 2, 9i, and minus 2 plus 4i, and I want its adjoint. I want you to send in the chat what you think the adjoint of this matrix is. This matrix is not unitary, not at all, but I want to know its adjoint. And let us know in the chat what you think the the adjoint of this matrix would look like. I'll wait a little bit for you. If one of you already wants to propose the first component of this matrix, let us know. Maybe I'll start with the first component because the first component was 6 minus 3i. So it's 6 plus 3i because we've changed the sign. What's the second entry? We got the right answer. It's minus 9i because we have the transpose. So these two get flipped. And we change the sign of the imaginary part. So the next one down here is 2, which only has a real part, doesn't change. And the last one is minus 2 minus 4i. So thanks for the answers in the chat. And you can try out on your own at home and see, for example, that the Harder-Matt matrix is unitary, the NOT one, the identity one here, this one is also unitary. And this is the condition here for unitary. So feel free to try this. Why do we need unitary matrices? In quantum computing, all quantum logic gates need to be unitary matrices for one reason. I'm able to create superpositions, for example, with the Harder-Matt gate. But when I build larger circuits, sometimes I create superpositions that I don't need later that I want to undo. And that's why all of my gates that I use, they need to be undoable or reversible. With classic binary computing, my NOT gate is reversible because I can just apply it again and then I have undone it. But the AND and OR gate, they are not reversible because if I apply an AND gate to 2 bits and I get 1 bit as an output, I'm unable to infer from the output what the inputs were. This only works for the NOT gate. But there's a whole branch of so-called reversible computing, And quantum computing falls into this. And with quantum computing, we're able to undo each operation, and this will help us to get rid of unnecessary superpositions. And with unitary matrices, we can do this because if we apply U and then U dagger, so the adjoint, what I get is the identity matrix, the neutral element, so to speak. So that allows me to undo operations. It's a new way of thinking because you haven't come across reversible computing a lot, I guess, before. But here in quantum computing, it's an essential foundation. In terms of the math, I think we've done most of the mathematics now. And now let's look at a couple of further consequences of quantum computing, as well as some of its applications. The adjoint we had just looked at is here, and here is part of showing that the Harder-Mudd gate is actually unitary because I have U dagger times U, it's the identity matrix. You would also need to show this for U times U dagger, because remember the matrix multiplication is not commutative necessarily, or not in general. So you would also need to flip them and say U times U dagger. And if that also leads to the identity matrix, then you have shown that a Harder-Mudd gate is in fact unitary. Now, after we have done this, let's think now, we've done the theory now, and there are way more gates and all of this, and I'll tell you later how you can learn more about this. But let's look at quantum computers now. So the theory I've just told you comes from the 1980s when quantum computing was proposed. But we need to build real computers on which we can run this. And this is something that has not existed in the 80s. And now quantum computers are available for the last 10 or 15 years. We will see real quantum computers in a moment. But implementing this in hardware is challenging because a quantum computer is keeps a quantum system. And if you study quantum mechanics, you will learn that a quantum system may interact with its external world. And this leads to decoherence. Decoherence means the quantum system loses its purity. Now, you could think about how can we isolate a quantum system from the external world? We cannot fully isolate it. So there will always be some decoherence. And decoherence means that we add more noise. We've already seen that there's noise or uncertainty from the measurement, because that's non-deterministic, and the decoherence as well. And the longer we run our quantum operations or our quantum algorithms, so the more gates we have, the longer it takes, so we get more decoherence because the quantum system interacts with the outside world. So you see, we have another factor of uncertainty in addition to the measurement. We are unable to fully isolate our quantum system from the outside world. And now you could think we want to isolate it as much as we can. That sounds interesting, but then we are unable to easily manipulate it from outside, because from outside we want to manipulate it and run operations, or choose which operations to run. We could do this very easily if we have little isolation, but then we would have too much decoherence. So we need to find a trade-off. And the current challenge when building real-world quantum computers is the number of qubits. There are some machines from IBM, they have a few dozens of qubits. And obviously we want to get to tens of thousands or even millions of qubits. But it's been noticed the more qubits you put together in a quantum computer, the more decoherence you get. So what can we do? We can run the same experiment many, many times because we have decoherence, plus we have uncertainty from the measurements. Or we could think about, for example, error correcting codes. It's another approach. And this is currently all actively being investigated in research and development, hoping we can build larger quantum computers with more qubits. There are various streams in quantum computing. And there is one approach which is a bit simpler. It's called so-called quantum annealing or adiabatic quantum computing. It's not a universal model of quantum computing, but it's a more constrained approach. But a company called D-Wave has made progress with this in the last 10 to 15 years. And they have started to sell quantum computers before IBM started to sell universal approaches. D-Wave implemented so-called adiabatic quantum computing or quantum annealers. And the good thing is, real quantum computers exist nowadays. Like 20 or 30 years ago, you had to use simulators, and you can use simulators today. For example, Qiskit. It's a library from the IBM world, for example. And you can simulate, but it turns out you can only simulate very small quantum systems on computers, not large ones. And with libraries like Qiskit or libraries from D-Wave, which is the adiabatic quantum computer, you can simulate on your computer, but you can also switch to a real quantum computer so that your code is run on a real quantum computer. If you buy a system from D-Wave, a few years ago they had the 2000Q, now they have other machines as well. The 2000Q was considered quite spectacular a few years ago. This one has 2048 qubits. Now I told you IBM has an approach with dozens of qubits or a few hundred. The IBM approach is universal quantum computing. D-Wave does adiabatic quantum computing. But I still find the numbers from D-Wave impressive. So they have 2048 qubits. And they're not all interconnected. I also need to highlight this. And the actual chip for the computations is made of a metal called niobium. And if you cool niobium down to 15 millikelvin, so 0.015 Kelvin, which is close to absolute zero, so something like minus 273 and something Celsius, then niobium becomes superconductive and allows you to run quantum mechanical effects. If you want to buy such a machine from D-Wave, probably you need to spend $15 million plus at least $1 million per year on the cryogenics. But it turns out you can also access computing time through the D-Wave cloud. So you can run your code in a simulator or on a real quantum computer that runs with D-Wave. They give you a little bit of computing time free per month. When I created these slides a few years ago, they gave you like 1 minute of computing time free per month. You can buy more computing time. Nowadays, if you create an account, you get a little bit more computing time, but the seconds are the seconds what's run on the quantum computer. And this was a small experiment as a demo. You can type it in something like a Jupyter notebook and run it in the D-Wave cloud, and you can run it then through the cloud on a real quantum computer, which took like 0.3 seconds. I think it was like 1 free minute. Yeah, not 1 free second, 1 free minute per month. And this took like 0.3 seconds to run. And if you run out of computing time, you can buy more time. So you don't need to make that investment upfront. And over the years, D-Wave started selling more quantum computers. For example, there was the Advantage 2 prototype that appeared about a year ago. It has 1,200 qubits, not more than 2,000 in the D-Wave 2000Q, but a different architecture and more couplers, meaning higher connectivity among selected qubits. And they claim this one is 20 times faster than the advantage QPU, and the advantage one claimed it's like 10 times faster than the D-Wave 2000Q, so 200 times faster. But anyway, these are often promotional numbers for specific use cases. One would need to analyze this in greater detail. But we see it's an active field where D-Wave keeps producing and selling more powerful quantum computers, and so do IBM as a different vendor. It's small, so you can zoom in. This is the IBM quantum computing roadmap, um, the version from a few months ago. Last year, they have now reached a quantum computer with 133 qubits, but it's universal quantum computing. This year, they want to get to 156 qubits, and over the next few years to more qubits, but also higher connectivity among the qubits. Plus, they want to advance with their software stack and a couple of other services, error correcting codes, and other things. So this roadmap, obviously, these roadmaps, they always need to be taken with some distance, with some caution, because they're also sort of marketing, but they are advancing and they are building more powerful quantum computers with more gates, with more qubits, and so forth. And you see in 2033 plus, they want to reach 2000 qubits. We need to see if this happens because it's not just an engineering issue, it's a science issue, and lots of fundamental theory needs to be, or lots of fundamental progress needs to be made. Aside from theory, these things need to be able to be built. Last year, I gave a speech at a quantum computing event in Switzerland, together with the lady who is in charge of quantum computing at IBM, who runs a big department for quantum computing. And I know her from that event and from other events before, and it's just very impressive to see the progress they have made in the last few years. Yet we need to have probably way more qubits in the future in order for this to run on real world large scale use cases. And it's a bit unclear when this kind of stuff could appear. Maybe faster, maybe slower. We need to see. But the reason I'm teaching quantum computing here in this course is you will graduate in maybe 2 or 3 years, or 4 years if you do a master's. And quantum computing will probably become more important in the coming years and decades. So it could also affect your career more. So the best thing you can do today is to have the foundation so you're able to keep track of what's happening in the quantum computing world, because it may impact your job and you may need to write code for a quantum computer in the future. But we're still at the very beginning. Now, we've seen how qubits work. We've seen quantum computers. Now let's look at concrete algorithms. And over the years, dozens of quantum computing algorithms have been proposed in the literature. Most of them we cannot run on real quantum computers yet because we need bigger quantum computers. They're still extremely limited today. But in most quantum algorithms that were proposed in the past are largely theoretical, largely for toy problems and not too much for real-world problems. But there are two quantum algorithms that are super interesting and more useful for real-world problems. And we'll quickly talk about them. So one is Grover's algorithm. Imagine we have a black box function. A black box function means it does something, we can see its output, but we don't know why it does that or how it works. And imagine we can pass n distinct values to the black box function. So 1 to 1000. And one of the inputs is the correct one. And the black box function will tell us for every input, yes or no. Yes means correct. No means not the value I'm looking for. And for exactly one of these inputs, the black box function will tell us yes. Now I want to find that one input for which the black box function says yes. With classical computing, obviously the best case is O of 1 because maybe the first input I'm putting in is yes and I'm done. But in the worst case, I need to put in all n values up to the last one, and the last one may be the correct one then. In average, this is O of n half, but the worst case is really O of n. And since I don't know how the black box function works, I'm unable to do any sort of ordering strategies or binary search, whatever. Do you think from traditional computing I can do better than O of n? Green sticker would mean with traditional computing, yes, I can solve this better than O of n, or red sticker would mean no, I'm unable to do this better. Please send me your response. And it's correct. All the answers you sent are no. With traditional computing, I'm done here. And this black box search is actually highly generic. I can use this for lots of different optimization problems because I have a list or a set of candidates, and one of the candidates is the optimum, for example. So I can use this highly generically for optimization. Now, with traditional computing, I'm unable to advance here. But with the so-called Grover's algorithm, I am able to do this better with a quantum computer. And not just better in terms of a constant factor, but better in terms of the complexity class. Using a quantum computer and Grover's algorithm, I am able to do black box search in O of square root of n. If you feel this is impressive, send some reaction, maybe some positive reaction if this surprises you that this is possible. And it's super interesting that this is possible using a quantum computer. Very importantly, this is a probabilistic algorithm. It may give us a wrong result. But when I have the result, I can just plug it in the black box function and see if the black box function really returns true. And if it returns no, I have a wrong result. So I need to run the quantum algorithm again. Maybe a few times, but not very often here because it's probabilistic. But actually with high probability, I get a solution that is correct. And actually the Grover's algorithm is like a pi divided by 4 times the square root of n many steps. So it's O of square root of n. With high probability is the result correct, and I may need to run it again. Now, if n is 1 million with a traditional computer, it's O of n. Now, if n is 1 million, the square root is 1000. So you see, I get actually a massive speed up. It's a squared speed up that the Grover algorithm gives me, and it's highly generic. I'm unable to run Grover's algorithm today for large inputs or any reasonable inputs on a quantum computer. For this, I need quantum computers with way more qubits. So most of this here is so far theoretical, but it's been proven that the Grover's algorithm works. And as we get bigger quantum computers in the coming years and decades, we can probably run this algorithm for larger and larger instances. But we need bigger quantum computers, and there are lots of physical challenges for this. Now, with a quantum computer, it would be great if there are algorithms that come even with a better speed up than O of n squared. Than O of n, well, just ignore the O. So we actually want something better than a squared speed up. We actually want something that maybe comes with an exponential speed up. And there's one algorithm for this, which is not a toy algorithm, but an algorithm that is actually useful for a real-world problem. It's not that generic as Grover's, but it's the Shor's algorithm. And imagine I have an integer n, and it's the product of two prime numbers, p and q. So p and q are prime numbers, and n is the product of these two prime numbers. What I want to do is, I have n, and I want to know p and q. With traditional computing, at least in a naive way, this takes an exponential amount of time to find p and q. And that's why today's encryption works well, because we have large keys, and that's why it's very difficult to break today's encryption. It turns out for classical computing, there is a so-called general number field sieve that could be applied here. And this general number field sieve is O of E to some product that I will not read out here. And you don't need to know this by heart, but you could write this, for example, on your cheat sheet or your note sheet for the exam. And this general number field sieve runs in sub-exponential time, a little bit better than a naive approach and with some constraints. And now I want to speed this up with a quantum algorithm. And Shor's algorithm actually runs in polynomial time. Concretely, O of this here, log n squared times log of n times log n. This is a polynomial eventually. And what I get is an almost exponential speedup. Now I can do the integer factorization much faster than before. And that would destroy most of today's encryption algorithms because they rely on integer factorization being very tough. Now, if we get larger quantum computers that work on large integers, then we could very efficiently run Shor's algorithm, do very efficiently the integer factorization, and crack most of today's encryption algorithms. Not all, some are not based on this principle, but most. And that's why in the last few years, new encryption algorithms got standardized. They're being implemented now by more and more IT vendors in order to be prepared that once today's encryption can be broken by having larger quantum computers available, we have already transitioned to new encryption algorithms and then probably not be much infected by this. And there are new quantum safe encryption methods available that cannot be cracked efficiently by a quantum computer. What I wanted you to see today is that quantum computers are very helpful for specific problems, but you've seen challenges like decoherence, measurement, low level of abstraction, a limited number of qubits, and decoherence on top. But in the coming years, there will be progress. We don't know how quickly and when, but quantum computing will affect your career in some way in the coming decades. And that's why I've added this here at the end of the course, that you get an outlook of what's happening in the market right now. The two interesting algorithms are Grover's algorithm and Shor's algorithm, for which quantum computers provide a speed up. Shor's is for integer factorization, but a near exponential speed up. And Grover's is a highly generic algorithm and comes with a squared speed up. Squared speed up is great, not as great as an exponential one. And there are more resources in case you want to read about this. There are books about quantum computers for machine learning. There's a very interesting website. It's quantum.country. These are very interactive essays They teach you something. There are some questions. Um, I published a book some years ago, and one of the chapter authors is Daniel Akenina, and he contributed a chapter on quantum technologies, which is a bit more than quantum computing. Daniel is one of the CTOs of Microsoft, and he contributed his chapter to my book, which is a very interesting chapter, and I think I have it available for you in Nextcloud. I've just checked it. It's available there in case you want to read the chapter. And Daniel is a phenomenal CTO at Microsoft and has a very good background in quantum computing and quantum technologies as a whole. So he contributed this here. Obviously, these further readings are not relevant for the exam. Yet sometimes I quiz you a little bit about quantum computing in the exam, about the things we have discussed so far. So what you need to know is qubits, constraints of qubits, quantum logic gates, just as an example, and have a bit of an understanding of unitary matrices, joint matrices, and decoherence and different computing approaches that we have looked at, as well as these two algorithms. We have now finished this lecture. I'll say something about the exam in a few minutes. Most of you are in one of our AI programs, either the English language or the German language program, so you will be dealing with me in the future again. I teach in the 4th semester computer vision. I teach one of the internship accompanying courses in the 5th semester. My course is called Innovation Management for AI, which I show you how to commercialize AI and build a bridge from a prototype to a product to a service that earns money. Computer vision, we build vision systems. In the 6th semester, I teach the AI project, which is a big group project in which we work with industry on real data. This year we have worked largely on computer vision use cases, but every year it's different projects, and we work with real industrial partners on real data. If you don't study in one of our AI programs, but you, for example, are in the cybersecurity program or one of the other programs, you can take most of these courses as electives if you wish. I also teach the big data course. It's also in the 6th semester, but most likely I won't be teaching it any longer because I have too many courses, and we've just hired a new professor, and she will most likely be teaching big data as of next year. And in addition to these mandatory courses in the AI programs, I teach an elective on quantum computing. So in case you want to learn more about quantum computing and its details, I have this elective. I always teach it in the winter semesters. All you need to know is programming, algorithms, complex numbers, and linear algebra. So you could already take the elective theoretically next semester in the winter if you wish, or later in your studies. But the course is super popular, and I have a few hundred students every winter who want to take it. Because there are seminar presentations at the end of the term and there are group presentations, we are only able to accept like 100, 120, maybe 150 students at the very most, and it's an elective. So I wish we could accept 400 or 500 students into the elective, but it's just we're unable to do that many seminar presentations. And it's first come, first served. Once the course appears in iLearn, the first 120 or 150 students who sign up can join the course. If you don't join the course, you can find all the recordings on YouTube as well, in case you want to learn more about quantum computing. We do lectures the first half of the term and then the seminar presentations. And there are obviously lots of other AI courses if you're enrolled in our AI programs, like AI programming, AI seminar, assistance systems, autonomous robotics, deep learning, machine learning, natural language processing, and so forth. And I think these courses in total will give you very good background in AI, and I hope you have enjoyed this course and learned lots of new stuff. Um, Lots of students have submitted their mandatory and their bonus problems already. I've reviewed them yesterday and today. All the submissions that I received so far are okay. Please check that you have really made your submission before the deadline, because every year there's some students who claim they have submitted, but it didn't arrive. After you submit in iLearn, please check again that your submission is really in it, that because I don't think there are bugs with iLearn necessarily in that regard, but students probably didn't click submit or whatever. And you need to submit until the end of July the 1st, and there are no late submissions possible. And in addition to this lecture, we have the lab sessions for the coursework. Today in the morning and afternoon, we had the last lab sessions, and there were quite some students who discussed their coursework with me. For quantum computing, there's no specific coursework. Just be familiar with the stuff we have discussed today. That's more than enough for the exam. And with regards to the exam, um, in my Nextcloud, you find all the past exams. And next week, Friday, we will meet at 8 o'clock in our lab, not to work on the coursework, but we will work together on last year's exam, which is the summer term exam, so the regular exam, not the recent one from the winter. And I have put printouts in the lab, so you can take printouts there if you wish. And we will meet at 8 o'clock only on campus, not online. I want you to be on site for the discussion. And what I will not do is to show you how upfront how to solve this exam. Rather, you would prepare this until next Friday. You can print it at home or take one of the copies we have available for you. And then you would be discussing your solutions with me. Rather, I would like to see maybe you have tried solving something on your own and you want to present that solution at the whiteboard. We'll discuss it with the other students. I'll provide you my input. If you really struggle to solve one of these problems, I can obviously assist you, but I will not provide all of my solutions up front because I want to engage in a discussion with you. So please familiarize yourself with last year's exam. And if you have any other questions on the course or the coursework, whatever, we can discuss this. But I want you to be punctual on Friday at 8 a.m. So we'll start discussing the exam at 8, and if you come in at 8:30, we will probably have finished the first few problems and we will not rediscuss them. And if no one shows up at 8, I'm not waiting for you, I'll just head home. So don't be late on Friday. The exam is certainly doable. This year's exam, if you're familiar with the content, if you have done of the lectures, if you have done the coursework, the tutorial sessions are quite helpful that are being run by my teaching assistant. Look at last year's exam as well as the other past exams, and then I think overall there's lots of material for you to prepare. And we've done quite a lot of content, but it all builds on top of each other. So make sure you're familiar with the foundations before studying the more advanced topics. Are there any questions? If so, maybe just raise your hand in Zoom. With there not being any questions, we are done for today. And I wish you a great weekend, and I look forward to seeing all of you next week, Friday, to discuss last year's exam. Take care and goodbye.